नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आपका स्वागत करता हूं हमारे YouTube चैनल केमिस्ट्री एकेडमी फॉर IIT JEE एंड नीट। टुडे दिस इज द सेकंड एपिसोड ऑफ रियल गैस वेयर वी आर गोइंग टू डिस्कस अबाउट intermolecular interactions. In the last class we covered two types of interactive forces acting between the molecules, attractive and repulsive forces. Today we'll discuss about attractive intermolecular forces, which is also known as Vanderwaal forces. In the last class we have covered that intermolecular forces act between two molecules. Ion dipole interaction is not intermolecular forces. Intermolecular forces is of two types, attractive and repulsive. So today we are going to discuss about attractive intermolecular forces. Attractive intermolecular forces are also known as van der Waal forces. Van der Waal forces are of three types. So the first type of van der Waal force is known as dispersion forces or London dispersion forces, or sometimes we'll say London forces. It acts between two non-polar molecules. These forces are also known as induced dipole forces. So let us discuss how this induced dipole forces are going to act. So initially if we take a non-polar molecule, due to symmetrical distribution of charge there is no polarity. When the molecules are far apart there is no interactive forces, but when the molecules will come nearer to each other, due to force of attraction between nucleus of one molecule and electron cloud of another molecule and vice versa, and simultaneously there is repulsion between the nuclei of two molecule and the electron clouds of two molecule. Because of that there is distribution of charge, and because of that distribution of charge there is polarity in the molecule. This polarity is temporary, so these are known as temporary dipoles. So in our NCERT they have mentioned that when atom A and atom B are far apart, the distribution of charge is symmetrical distribution of electronic charge cloud. But when they will come nearer to each other, there is a development of instantaneous dipoles or induced dipoles between A and B atoms, and because of that there is interactive forces. So when the molecules are coming nearer to each other, initially these attractive forces will dominate, and a time will come when repulsive forces will dominate. These forces act in solid, liquid and gaseous form of the substance. Let us take an example. When we are discussing about halogens, we know that fluorine, chlorine are gases at room temperature, bromine is a liquid and iodine is solid. So chlorine molecules in gaseous state at room temperature are non-polar molecules, and between them there is van der Waal force of attraction, and that van der Waal force of attraction is induced dipole attraction or London forces or dispersion forces. Similarly, bromine is a liquid, and with bromine is made up of same type of atom. It is linear, element will be 0, so it is a non-polar molecule. Bromine molecule are in liquid state at room temperature, and definitely the liquid state of bromine molecule is because of the force of attraction between bromine molecules. Because of London forces, bromine exists in liquid state. And similarly we can say iodine is a solid. So iodine molecules are in solid state at room temperature is because of London dispersion forces or induced dipole forces. There are four factors which affect London forces. The first factor is London dispersion forces is directly proportional to the number of polarizable electrons in the molecule. The second factor is London dispersion forces is directly proportional to molecular weight. The third is it is directly proportional to molecular size. And the fourth factor on which London dispersion forces will depend is surface area available for interaction. In case of noble gases, as we are moving down the group from helium, neon, argon, krypton, xenon and radon, their molecular mass is increasing down the group, and as we see their boiling point is also continuously increasing down the group, and these all atoms are non-polar in nature. The boiling point can be explained by London forces. As we are moving down, their molar mass is increasing, the number of polarizable electrons are increasing, their size, molecular size is increasing, and their interactive surface area is also increasing. So all these four factors helps to increase the boiling point as we move down the group. Same way when we are discussing about halogens, fluorine, chlorine, bromine and iodine. In case of fluorine, chlorine and bromine, if we discuss that what is the boiling point, as we move down the group, their molar mass is continuously increasing. Fluorine has 38, chlorine has 70.9 and bromine has 159.8. And their boiling point is also continuously increasing because they are non-polar molecules. The interactive forces acting between them is induced dipole, or we can say London forces. And because as the molar mass is increasing, the polarizable electrons are increasing, the surface area is increasing, the interactive surface area is increasing. Because of that, the boiling point of these molecules are increasing down the group. With the help of Vanderwaal forces, we can also explain the vapor pressure of liquid. Like if we do comparison between the vapor pressure of C6H6, that is benzene in liquid state, and toluene in liquid state, these compounds come in liquid solution. So the boiling point of toluene is greater than the boiling point of benzene, and again it can be explained on the basis of Vanderwaal forces, and especially these Vanderwaal forces is acting between non-polar molecules. Both are non-polar. So London forces, because of that, as the benzene has less molar mass than that of toluene, or we can say that the surface area for interaction of toluene is greater than that of benzene, so benzene is more volatile than that of toluene. And if the vapor pressure will be more, the boiling point will be less. So we can say that benzene has less boiling point than that of toluene. The second type of Vanderwaal forces is known as dipole-dipole forces. They act between the molecules possessing permanent dipoles, that is polar molecules. These are also known as Keesom forces. Polar molecules can interact by London forces also. We know that if we discuss about hydrides of halogen like HF, HCl, HBr and HI, all these molecules are polar in nature due to difference in electronegativity of hydrogen atom and fluorine atom. So HCl is a polar molecule, and because of that electronegativity difference, the shared electrons will be shifted towards chlorine atom, and because of that there is a partial negative charge on chlorine atom and there is a partial positive charge on hydrogen atom. And in chemistry, when we denote the sign of dipole moment, it is from positive charge towards negative charge. So this is the sign of dipole moment. So there is dipole moment in HCl molecule and it is permanent. So between one HCl molecule and another HCl molecule, there is dipole-dipole attraction. Hydrogen bonding is a special case of dipole-dipole interaction. We know that what is the condition for hydrogen bonding. In most of the cases, when an hydrogen atom is attached to nitrogen atom, oxygen atom or fluorine atom, and then this hydrogen atom come in contact with another nitrogen, oxygen and fluorine atom, then there is formation of hydrogen bond. Like here we are with some examples like ammonia. Between two ammonia molecules there are hydrogen bonds. Similarly, between two water molecules there are hydrogen bonds, or between two hydrogen fluoride molecules there is hydrogen bond. So hydrogen bond is a special case of dipole-dipole force of attraction. In NCERT they have given an example where they are saying that HCl molecule has a permanent dipole, and because of that there is dipole-dipole interaction between two HCl molecules. Same way we know that water exists in liquid state and also at lower temperature it can convert it into ice. So this is the structure of solid form of water which has case-like structure. In this structure we can say that one water molecule is attached with four water molecules through hydrogen bonding. So one water molecule here I am showing that it is attached with four water molecules through hydrogen bonding, and it is a case-like structure. So this case-like structure of ice is because of hydrogen bonding. In liquid state also water can form hydrogen bonds. Now we know that HF at room temperature is a liquid, but it can also exist in solid state, it can also exist in gaseous state. So HF is a substance which can do hydrogen bonding in all the three states. In gaseous state it can do hydrogen bonding, in liquid and solid state also. So a stronger hydrogen bond to exist in liquid HF than water. So they are discussing that hydrogen fluoride can form a stronger hydrogen bond because the electronegativity of fluorine is greater than that of oxygen, and because of that the hydrogen bond is strong. But the boiling point of water is greater than the boiling point of hydrogen fluoride. So they are saying that the boiling point of HF is lower than that of water because each water takes part in 4 intermolecular hydrogen bonds. The number of hydrogen bonds with which water is attached is more than that of hydrogen fluoride, and because of that the boiling point of water is greater than the boiling point of hydrogen fluoride, though the hydrogen bond formed by hydrogen fluoride is greater than that of water. So here this is a zigzag structure and it is liquid form of hydrogen fluoride. Hydrogen fluoride also form the same type of structure in solid state, zigzag structure. And in gaseous state it exists in cyclic form. So here they have mentioned that in gaseous hydrogen fluoride, many of the hydrogen fluoride molecules are associated into cyclic. One of them is HF6 structure of the type pictured here. So it can also exist in 2 molecules combined or 3 molecules combined. It exists in cyclic form. So dipole-dipole interactions can exist in solid state, can exist in liquid state, can exist in gaseous state. In this diagram it is shown the boiling point of hydrides of oxygen formally, and here that water has highest boiling point than H2S, and H2S has lower boiling point than H2SE, and H2SE has lower boiling point than H2TE. So the boiling point of water is greater than the heavier molecules in oxygen family, and it can be explained by hydrogen bonding. Similarly, hydrogen fluoride has more boiling point with respect to HCl, HBr and HI, and the reason is same. Hydrogen fluoride can do hydrogen bonding, but HCl, HBr, HI cannot do hydrogen bonding. And in the same way we can say that ammonia here has more boiling point than the hydrides in its group. So PH3 has less boiling point than ammonia, and then arsenic hydride has more boiling point than PH3, and finally if you see SbH3 has more boiling point than ammonia. So how we can explain that ammonia and SbH3? How we are going to say, because in case of SbH3 there is no hydrogen bonding. This SbH3 molecule is polar in nature, so there is dipole-dipole force of attraction. Along with dipole-dipole force of attraction there is London forces also, induced dipole force of attraction, which depends on molar mass. Greater the molar mass, more will be the London dispersion forces. So when we are talking about SpH3, the net interactive forces in SpH3 is because of dipole-dipole interaction as well as induced dipole interaction. And in this way we can say that the boiling point of SbH3 is greater than that of ammonia. In case of hydrides of carbon family, there is no hydrogen bond and there is no dipole moment because these molecules are non-polar. So as the molar mass is increasing or surface area is increasing, the boiling point is increasing. So this can be explained by London dispersion forces or induced dipole interactive forces. Here this is a DNA structure. So the DNA double helix in which 2 polynucleotide chains are linked together by hydrogen bonds between adenine A and thymine T, and between cytosine and guanine there is hydrogen bonding. So these are nucleic acids which are attached, A and T are attached by hydrogen bonding, or G and C are attached by hydrogen bonding. So the double helix structure of DNA can be explained by hydrogen bonding. This is also the same thing. They are saying that hydrogen bonding between guanine and cytosine. So they have shown the structure here that there are 3 positions where hydrogen bond can take place between guanine and cytosine, and this is the structure of the same thing. So this is double helical structure where A and T there is hydrogen bond. So here they have adenine and thymine. At what portion there is hydrogen bond? And similarly between C and G cytosine and guanine, there are 3 positions where hydrogen bond can take place. So the double helical structure of DNA can be explained with the help of hydrogen bonds between the nucleic acids. When we study liquid solution, in liquid solution there is a fixed question that when acetic acid is added to what, we will find what is the molar mass of acetic acid. We will find the molar mass of acetic acid is nearby 120, double what we are expecting. The abnormal molar mass of acetic acid can be explained by hydrogen bonding between 2 molecules of acetic acid. Because of their structure, they can dimerize, and because of this dimerization, we can explain the abnormal molar mass of acetic acid in liquid solution. Here again, the surface tension of water or surface tension of different liquid is also related to intermolecular forces. Here in this picture, they are showing that the molecules which are present in the bulk are attracted from all directions. So the net force acting on this molecule is equal to 0. But the molecule which is present at the surface has net downward forces because it is not surrounded from all directions. The molecules present at the surface are feeling a force which is acting downward, and because of that there is a surface tension in a liquid. So water has hydrogen bond, and that hydrogen bond is dipole-dipole force of attraction, and it is a strong force of attraction if we discuss within Vanderwaal forces, and because of that water has more surface tension, and because of the surface tension of water strider is able to walk on water. So like if a person is moving on a rope, if the tension on the rope and the strength of that rope will be more, the person can climb on that. Same way, this water is, because of surface tension, it is able to allow the water strider to walk on it. There are other things. There is hydrophobic nature of the legs. There are hairs on the leg of this water strider. So with the help of hydrophobic nature of the legs and the balancing, because you can see that legs are big and there is balancing, so it is covering a large surface area, it is able to move on water. So again, it is related to intermolecular forces. Viscosity of liquid and gas can be explained with the help of intermolecular forces. Vapor pressure of liquid, like if I am talking about water, if the interactive forces between water molecule will be more, then the molecule present at the surface has less tendency to go in vapor state. If the interactive forces between the liquid molecules will be less, it can easily vaporize. The vapor pressure also depends on intermolecular force of interaction. Now this is one of the most important point which we should understand. Like here there is a diagram. This diagram is taken from some standard book. I don't remember the name, but on the y-axis there is energy, and on the x-axis different molecules are given like argon, carbon monoxide, HI, HBr, HCl, NH3 and H2O. And they are discussing the type of forces acting between the molecules of these chemical species. The dipole-dipole forces are indicated by in dark blue color, and dipole-induced dipole forces in light orange color or peach color. Yellow forces is for induced dipole interaction, and the total force, sum of all these forces, is represented in sky blue color. So if we discuss here, like in case of argon, only yellow color is there and there is no other interactive forces, only induced dipole interactive forces is there, because argon we know that it is non-polar in nature. Same way for carbon monoxide is polar, but the polarity is very less. So you can see here that because of that polarity there is no net interactive forces. So again it is behaving like that non-polar molecule. And same way we are discussing for HI. In case of HI, due to polarity, because the difference in electronegativity of hydrogen and iodine is not much, but because of that there is a very small quantity of dipole moment interactive forces, but most of the interactive forces acting between HI molecule is induced dipole interactive forces. Same way we can discuss about HBr, HCl. As we are moving here, the electronegativity difference between H and Cl is more than H and Br. So that's why dipole-dipole interaction in case of HCl is greater than that of HBr. But the molar mass of HBr, HCl and HI has the biggest molar mass. That's why induced dipole interactive forces is highest in HI, then in HBr and then in HCl. In case of ammonia, we know that it do hydrogen bonding, but it is interesting to know here that due to dipole-dipole interaction, due to hydrogen bonding, this is the contribution of hydrogen bonding. And the yellow bar, you can see that this is contribution of induced dipole or London dispersion forces. So in case of ammonia, the contribution coming from induced dipole is greater than the contribution coming from dipole-dipole. So we should also learn that if I am saying that a molecule is polar in nature, that polar molecule has dipole interaction as well as induced dipole attraction. And sometimes in polar molecule, the contribution of induced dipole is greater than the contribution of dipole-dipole. Like in case of water, because strong hydrogen bonding and the number of hydrogen bonds are more in number, one water molecule is attached with 4 water molecules through hydrogen bond. Here we can see that the contribution of dipole-dipole force of attraction is greater than the contribution of induced dipole force of attraction. So this is very interesting that in a molecule, when the molecule is polar, along with dipole-dipole, there is induced dipole force of attraction also. But these things can be experimentally determined. We cannot predict that which type of interactive forces is contributing more and which type of interactive forces are contributing less. But this is a very interesting subject. So we can say that dipole-dipole forces exist in solid, liquid and gaseous form of substance. Along with dipole-dipole interaction, there is also induced dipole interaction exists between molecules, which we have seen in the graph. The third type of interactive forces is known as dipole-induced dipole forces. So in dipole-induced dipole forces, they act between polar molecules and non-polar molecules. It is also known as Debye forces. London forces also act between them. So one molecule has permanent dipole, another molecule is non-polar, so it will act like induced dipole. For an example, when we are discuss the solubility of inert gases in water, so if we take example of inert gas, we can say that helium is an inert gas, helium, neon, argon, krypton, xenon and radon. So when we discuss the solubility of these gases increases down the group. So we can say that helium is less soluble and radon is most soluble. So as we are moving down the group, the solubility is increasing. So these are non-polar molecules, and we know that in non-polar molecules, as the molar mass will increase, the polarizable electrons will be more, the surface area will be more, or the interactive surface area will be more, than the intermolecular interactions will be more. So we can say that with water, radon can form a strong bond as compared to helium. So the solubility of inert gases in water can be explained by these type of interactive forces, that is dipole-induced dipole force of attraction. Along with dipole-induced dipole interaction, there is also induced dipole interaction exists between these molecules. So if I am saying that if a molecule is polar, definitely it has induced dipole force of attraction along with dipole force of attraction. Earlier we have studied about Lennard-Jones potential, where the net potential energy can be written as the sum of two terms. The first term is related with attractive forces and the second term is related to repulsive forces. So all attractive forces, almost they are directly proportional to 1 upon r to the power 6, while the repulsive forces is directly proportional to 1 upon r to the power 12. Here between three type of Vanderwaal forces, what are those? The first one is induced dipole forces, the second one is dipole forces, and the third one is dipole-induced dipole forces. So these type of forces is acting between the molecules. So when we are talking about dipole forces, there are two possibilities. If the substance exists or the atom or molecule exists in stationary state, how we can say, like in water molecule, in ice, water is stationary because it is existing in solid state. So in those cases, in case of dipole where the molecule is stationary, it is found that the interactive forces is directly proportional to 1 upon r to the power 3. Otherwise, in general, when we are talking about any type of intermolecular interactions, the interaction energy is directly proportional to 1 upon r to the power 6. And in all molecules, the repulsive energy is directly proportional to 1 upon r to the power 12. Ion-ion interaction is not intermolecular interaction. We know that if a positive charge and negative charge is there is electrostatic force of attraction, and that we write that is equal to 1 upon 4 pi epsilon naught q1 q2 upon r. So the potential energy or interaction energy in ion and ion is directly proportional to 1 upon r. All these intermolecular forces are short range forces. When we are talking about attraction and repulsion, they are short range forces. But when we are discussing about the force of attraction between a positive and negative charge, it is a long range force. In the next episode, we will discuss some problems based on application of intermolecular forces. If this information is useful to you, please like and subscribe our channel. Thank you.